So we're looking at 6.1 for our homework assignment. We've got a whole bunch of problems to do, and then we got a couple questions from the equilibrium lab as well, and we'll look at those. I think I just messed up that alignment. I did. Close enough. Okay, let's go ahead and just do 6.1 in order. We'll start with number 7, even though unless you want to go first because you were here first. But
No.
Okay, so we'll just go in order. We'll go 17. We'll go 2, 7, 18, 19, 21, 23. Does someone have number 2 open and ready to go?
How much heat is released into the surroundings when 186 grams of ethylene C2H4 gas are burned to form liquid water and carbon dioxide gas? You'll need to look up the heat of formations from data and the things to calculate the standard heat of reaction as the first step.
Okay, so we're looking at this thing. Technically, we know this can be a double arrow. It's just very much going to be product favored. It's a combustion. This is going to be C2H4 gas. Combusted, so it's going to be O2 gas added in. We're going to make CO2 gas and H2O gas, assuming we have perfect combustion. We have to get a delta H for the reaction. This is kind of a review problem. I'm surprised I put this on 6.1. We have to get a delta H for the reaction, so we're going to do sum of products. Oh, wait, I'm writing the wrong thing. Sum of delta H of formation of products minus sum of delta H of formation reactants. All right, going back to like week 1 stuff. We need some tables for this. I can't do this in my head. We need data tables to get that delta H, get that delta H. We don't need delta S.
Then you just do products minus react. Like you do find it for one side and then so you just subtract it. Right?
Yeah.
There.
Did we get that part? I don't remember who asked this question.
With C2H4 the acetic acid?
Wait, was it acetic acid?
Oh, for me, it's an ethyl gas.
Oh, you're gonna have different randomized values.
Okay.
So it's gonna have different chemical compounds. It could be CH3COOH, it could be C2H4, it could be C2H6, it could be C2H2. I think there's like 6 or 7 different compounds that could randomly select. I think that problem even has the like change values and will generate new random numbers for you to practice more. So depends on what our random thing is. I don't have the thermodynamic table open, but we got to do products minus reactants. I can open it, but I need help. So at that point, we're doing that sum of products minus sum of reactants. Let me just pull. I am going to be a Luddite. Did you know you can get a print version of the textbook? It's just because I don't want to move my laptop while I'm recording. So I'm going to use the actual physical print version of the textbook. And find like the proper appendix. See ya. Which I believe is Appendix G. Yes, it is Appendix G. And we're going to find these different compounds. Let's see here. So now it's just like a C2H4 is 52.4. I'm just going to write these numbers down. 52.4. O2 I already know is going to be 0. Before I switch pages, let's see if CO2 is right here. CO2, negative 393.51. H2O. H2 gas is negative 241.82, negative 241.82. And we'll just, for giggles, we'll look at oxygen as well. How is this table organized? Where did they put their oxygen compounds? Aluminum, tin, cadmium, B. Because it's like mostly in alphabetical order, but then oxygen's not there. Oxygen compounds. C, D, OH. I wonder if they just don't list it because they're like, you already know it's 0, right? Oh, there it is. O2, 0. Right? All listed in kilojoules per mole. So then I just do sum of products minus sum of reactants. Oh, I didn't balance the chemical equation yet. That's going to get me in trouble right now. Right? This N and M, that's the molar coefficient, so I have to balance the chemical reaction. 2 carbons, I'll have a 2 there. 4 hydrogens, I'll have a 2 there. That worked out nicely. That's going to give me 2. That's going to give me a 3 here. Easy one to balance. Sometimes they're harder to balance, particularly if you end up with, well, let's not worry about it. Now we just do sum of products minus sum of reactants. So I'm going to have 2 times 3, negative 393.51 plus 2 times negative 241.82 plus, minus, getting my minus reactants, 1 times 52.4, and that is intentionally a positive 52.4, plus 3 times 0, which 3 times 0 doesn't really matter. We do 2 times 393.51 is 2 times 241.82. Okay, pretty big. Minus 52.4. You can double check my math, but I'm getting negative 1,323. Right? So it's an exothermic reaction. It's a very exothermic reaction. Not surprising because most combustion reactions are, I think all combustion reactions are very exothermic. I had to stop and be like, is there an exception to that? Is there a cold combustion reaction? I don't think there is. I think it's part of the defining features of combustion reactions. If you're watching this online, let me know if I'm wrong. I don't think so, though. Cold combustion would be weird. Endothermic combustion. No, that doesn't seem real. So can you remind me what the rest of the question was? We're looking at number 2.
It was how much heat is released into the surroundings? 186 grams of ethylene are burned to form liquid water and carbon dioxide gas.
So the next thing we have to do is we have to take that 186 grams, we have to get it into moles. Right? Fortunately, because of the 1 ratio, this is kilojoules per mole of reaction. But because it's 1 mole of C2H4 per reaction, this is also 132.3 kilojoules per 1 mole C2H4. I can do that molecular weight in my head because that's 12 plus 12 is 24 plus 8 is 28. So I just get 1/28 mole per gram. 186 divided by 28 gets us 6.64 moles of C2H4. Last step, multiply them together. I have 1323 kilojoules per mole times 6.64 moles. A whopping 8,788.5 kilojoules. Couple things. Did that make sense? Does that clear things up for you? I never like putting units like I did on this last line. I did this on purpose. I did it in a way I don't like on purpose to show you how confusing it can be if you're not specific with your units. You notice everywhere else I was specific with my units. Moles of what? Kilojoules, right? Here, kilojoules per mole of what is unspecific. 6.64 moles of what? It's unspecific. That's pretty unsatisfying. We can usually use the context of the problem to figure it out, but I really like to include C2H4 H4, C2, H4 there. So that way I know I'm treating my units properly. It also is like a nice hint to my future self when I'm looking back at the problem. So I don't have to rethink through everything again. I can look at it and be like, oh yeah, it's C2H4. Is that catching everything? That's catching everything. Okay. Now, the other thing you'll notice, I dropped a negative sign over here. And we have to be careful, right? So when it asks for energy released, it often means like that's the amount released, right? It's equal and opposite. So that's the amount, that's why I put released in quotes. This is the energy of the reaction. And then you can do the Q in equals negative Q out. So the energy released is going to end up being the positive version of that. Because the reaction generates that energy, and that energy goes to the environment around it. So drop the negative sign. The reason I put released, right, so the place where people can get in trouble and we have to be careful is if you have negative energy released, the word released there that I put in quotes is essentially doing the work of that negative sign. And so it ends up creating some amount of ambiguity if you have a negative energy released. It feels really, it's a double negative. It doesn't feel great to me. So I will usually either drop the negative sign and put the word released. I'll no longer have that be an equal sign, but I'll have that be like an arrow going to that. Or I leave the negative sign and I don't put the word released, right? I don't like to have that kind of like mathematical negative and then language negative in the same instance. Creates confusion. Good? Great, okay. On to number 7.
Yes.
So that was number 2. What does, we'll give me a moment to erase the board, but get number 7 up and ready to go. What's number 7 say?
Consider 4 reactions and call them A, B, C, and D.
Yeah.
And then you have to find the sign of delta H standard and delta S standard by either their positive or negative. So reaction A has a K constant that is greater than 1 at all temperatures. And then B, K is less than 1 at all temperatures. C, K is greater than 1 at low temperatures, but it's greater than, or no, it's less than 1 at high temperatures for C.
Okay.
And then D, K is less than 1 at low temperatures, but greater than 1 at high temperatures.
Okay. And I'll just put the K low and we'll remember it's the opposite for high. So we've got 2 where K is not changing, 2 where K is changing. So the way that we can work this out is recognizing that, oh, first off, how do we start this? Like, where do we start? Where do we begin? What do we know about K? What's the context? First off, these are all KEQs, right? These are equilibrium constants. How does K relate to delta H and delta S?
The ln of K
Yeah.
equals, would it be the Van Hoff equation?
Kind of. I'm going to do it as the not all the way Van Hoff equation. Right? I'm going to have, actually, even this confuses me too much. I'm going to do it as 2 separate equations. Right? I'm going to have delta G is equal to delta H minus T delta S. And I'm going to have delta G is equal to negative RT ln K EQ. And I'm going to think about it in 2 steps. It creates less confusion for me. Because both steps at once is just too much all at once for me. So if K is greater than 1 at all temperatures, that means, so reaction A, if K is greater than 1 at all temperatures, that means this is always going to be a positive natural log. Delta G is going to be always negative. If delta G is always negative, well, delta H has to be negative, right? Right, if it's always negative, right? So the thing I think about is first go to 0 Kelvin, right? Or really small Kelvin. This term completely disappears. So delta H, if it's going to be negative at all temperatures, even 0, delta H has to be negative. So I can tell from that delta H has to be negative. And then I say, well, what about at really high temperatures? At really high temperatures, like say temperature gets up to like 1 billion Kelvin. Not realistic, I know, but just for mental activity. Then this delta H is going to be small compared to negative T delta S. So if this is still going to be negative, delta S has to be positive. And then I just play that game for each situation. Right? I say, given the information, what does delta G have to be? What happens at really low temperatures, where it's only delta H? What happens at really high temperatures, where it's just negative T delta S? Let me just play that game for each one. If KEQ is less than 1 at all temperatures, that's going to be B. That's going to get us delta G is positive. That means delta H has to be positive and delta S has to be negative. And that will guarantee that we are positive always. If KEQ is greater than 1 at low temperatures, that means negative, negative. This one's going to be positive. Let me do that one slower, because that's one where it's actually interesting. Right? So if we look at C, and we say, okay, delta G at low temperatures is greater than 1. Delta G greater than 1, that's going to be positive. Delta G is going to be negative at low T. At low temps. Ah, the board is crooked. That's better. Okay, so delta G is going to be negative at low temperatures. Low temperatures means this term disappears, so delta H has to be negative. Because at low temperatures, that's the only way to guarantee that delta G is negative and K is greater than 1. At high temperatures, delta G goes positive at high temperatures. So at high temperatures, this negative T delta S term dominates. And the only way, if that delta H is gone, the only way that delta G can be positive is if delta S is also positive. Or sorry, if delta S is negative, so that negatives cancel each other out. So that's going to be negative, negative. And then part D is just the flip of part C. So it ends up being positive, positive. It's a little thought experiment. So that's number 7. Questions about that? Okay. Okay if I erase? That brings us to number 18. This should get more interesting.
Okay. So propanoic acid reacts with water.
Do I know what propanoic? Oh yeah, propanoic acid. Okay.
Yeah, it just gives the reaction basically.
Right. So propanoic is methyl is C3H345H5COOH.
It also just says use HA as shorthand for the acid.
Oh, we could use HA as shorthand for the acid. That's fine. I really like it. Some of my colleagues really don't like it. But HA.
Yeah.
It's a weak acid.
HA aqueous plus O2 or H2O liquid goes to with the 2 arrows.
Always 2 arrows now.
Yeah. A minus aqueous plus H3O plus aqueous.
Great. Now, I will say, I'm okay using HA and A minus, but if we're going to use HA and A minus, we should always define what are we calling HA and A minus. So in this case, right, that C3H5COOH, that's propanoic acid. Let me double check that real quick. One, 2, 3, 4, 5. Yep, good, okay. Just wanted to double check my Lewis structure. And then I'm going to have my A minus. It's going to be C3, Or this is supposed to be C2H5COOH. COO minus. That's what I'm calling A minus. Right? If we're ever going to use the HA, A minus shortcut, which I'm okay with, we should define what are we using for HA, what are we using for A minus. The reason I like to do that is because then when we look at this chemical reaction, this equilibrium we're considering, all weak acids are essentially going to have the same looking chemical reaction. So it simplifies the reaction, like the equilibrium math, the equilibrium kind of consideration. But it does depend on what chemical compound we're looking at. So, okay, so we got this. What's it ask next?
The K is 1.3 times 10 to the negative fifth. And then it asks for the equilibrium concentration of H3O plus when starting at 0.25 moles of propanolic acid.
0.25?
Yeah.
Perfect. So that's going to be our initial, which is going to be like our Q value. Right now, I assume it's asking about this in water, so these are going to be zero molarities. And we say, okay, my Q value is going to be products over reactants. I'm not going to worry about the pure water. I'm going to have 0 times 0 divided by 0.25. My Q is going to be 0. So that means when I look at my change step, I'm going to have to use up some of my reactants and create some products. Right, if we're looking at this in terms of our, Gibbs energy plots, we've got something like this. We know we are starting, our initial point is going to be at Q equals 0. Our equilibrium point is going to be someplace down that curve where we've got more products. So my reactants get used up, my products get created. I get a minus X on my reactant side, plus X on my product side. I'm taking a little more time with this because you haven't seen a problem like this before. But it's the same thing. Question?
Can I ask, how are we starting with Q at 0, but also the Q is 0.25?
Oh, that's not the Q. It's this entire line makes the Q. Remember, Q, if we're looking at, I'm going to do it in this bright orange color for fun. Q is going to be my A minus times my H3O plus initials divided by my HA initial. I'm going to get 0 times 0 divided by 0.25. That's still equal to 0.
So our reactants are on the bottom there, right?
Products over reactants, yes.
Where's H2O?
H2O is a pure liquid. We don't include, just like we
So
didn't
it's not
include
in
the
the
solid,
solution.
it's
Okay.
not in the solution, even though it technically makes the solution.
Yeah.
It's only, again, it's that kind of freezing that we talked about before, where it's like, I put this acid into the water, and I freeze time for a moment where the ball's at the top of the ramp, I'm still holding it.
Okay.
And I say, okay, it hasn't happened yet. Pure water isn't interesting, or, isn't active in the solution, but once it mixes, now I can see how the mixing happens, that increase in entropy, that change in the enthalpy, which we're hiding all of that enthalpy and entropy just in our equilibrium constant.
Okay.
So I fictionally hold our reaction up at the 0 point and say, oh, what happens when I let go? It changes. And it changes by breaking apart some of the weak acid to make this anion and this cation in solution. Right?
Okay.
Breaks apart into A minus and H plus. I'm going to erase this orange. And then we said, okay, when we finally get to equilibrium, I'm going to end up with 0.25 minus X. I'm going to end up with 0 plus X, which I'll just call X, and 0 plus X, which I'll just call X. My Ka expression is going to be products over reactants. It's going to be A minus at equilibrium divided by the H3O plus at equilibrium divided by my HA at equilibrium. It's nice, it's all a 1-to-1 mole ratio. I can then go ahead and start plugging in what all of these values are noticing that box in green is the equilibrium conditions. So I'll write this first down in the explicit way of 1.3 times 10 to the minus 5 is equal to x times x divided by 0.25 minus x. And that would be the explicit kind of solve it. This gives us a quadratic, though. Don't like quadratics. Unless you do. Do you like quadratics? Who likes quadratics? I kind of do. So much thing in the natural world, so many things in the natural world follow quadratics. It's wild. You get these squared things everywhere. In any case, we look at this and say, okay, there's got to be a shortcut. And we say, look, Ka is really small, right? 1.3 times 10 to the minus 5. That's really small compared to 0.25. So I'm going to use the x is small approximation. And I'm instead going to say 1.3 times 10 to the minus 5 is approximately equal to x squared over 0.25. And that's much easier to solve.
There's like an equation solver in, like, if you have a TI, so it just does it for you.
For the quadratic?
Yeah.
Yeah. X is small, but will it do the fifth roots as well?
I think it does everything.
Probably does.
I think it was like Math 5 or something.
Yeah.
We don't need to though, right? The nice thing, the x is small approximation is this really wonderful approximation founded in physical reality. So we can look at this and say, look, based on physical reality, we don't need to solve the quadratic. Right? I can look at this and I can do 1.3 times 10 to the minus, not 13, 1.3 times 10 to the minus 5 times 0.25 square root. And I think the amount of time it would take you to plug in the quadratic is going to be longer than what I just did.
No.
Well, I started after you.
Well, it's pretty
1.8
easy.
times 10 to the minus 3?
Um,
What'd you get?
maybe it's because my calculator's in parametrics. Maybe I have to change that first.
No, that should be fine. Question?
Can you go over why we're finding that minus x like negligible on the?
Yes, we'll do that in just a
Okay.
moment.
Wait, what did you get?
I got 1.8 times 10 to the minus 3.
I
I got
plugged
that
in the
too.
wrong one. That's
Yeah.
why.
Okay. Did you get that with solving the full quadratic?
I used it with the approximation.
It's really 24.
No, that's not right. X is not equal to 24. How is this getting 24 for your answer?
Because it's x squared over 0.25 minus x.
That's right, but that answer is not correct.
Hmm.
I mean, we could try back solving it, right? We could plug in 24 squared divided by 0.2. 0.25 minus 24 is going to give us a negative number. Like, that can't be right. So maybe you shouldn't use that solver, and we should just do
Maybe
the
I
small
used it wrong.
approximation. It could be you used it wrong, I'm not sure, right? One of the problems is every one of these calculators, we can look at it later as well, but every one of these calculators has a different system for setting up their like solve equation thing. I use an online solver called Wolfram Alpha that I really like when I'm double checking my work. If I want to do an actual percent error, we need to compare the exact answer to the approximate answer. Most of the time, just a percent difference check is fine. So using the x is small approximation, so we don't have to be like, am I using my calculator correctly? I get 1.80 times 10 to the minus 3. And I can tell that's going to be my propanoate anion, my hydronium anion, my H plus cation, sorry, not anion. And it's going to be how much my HA gets subtracted by. And this is where we can say, oh, x is small, right? Approximation works. So when we're looking at this, so we made an approximation saying, I don't think that x, because my Ka is a small value, that tells me I only need to make a small amount of products. I only need to use up a small amount of reactants for this to work out. And so I look at this and I say, okay, if I did 0.25 minus 0.0018, that's approximately 0.25 still. Now, technically, that's not exactly true, right? If I did, I should do 0.2482. It's actually exactly equal to 0.2482. So how much error did I just introduce? Not that much. And so the thing that becomes important for us is x approximate divided by concentration initial has to be less than 0.05. That would be, this is not technically percent error, that would be a small percent difference. So I can take my 1.8 times 10 to the minus 3 divided by 0.25, and I get 0.0072. Right? I'm going to introduce some error, but not very much. And it saved me solving a quadratic.
I guess I'm still a little confused on how you come to that conclusion that x is going to be very small.
I kind of eyeballed my initial concentration of point. Now, small is relative, so it's a really good question, right? Small is relative.
Wait, so you divided the x approximate by 0.25, or what did you divide it by?
Yeah.
Okay.
Right, so in this situation, that would be my HA concentration explicitly. I usually just leave it blank because it changes for which problem we're doing. Right, in this situation, that would be specifically my initial HA concentration. I just eyeballed it. I just kind of said, look, 0.25 is really big. So I'm comparing my HA to my initial concentration to my Ka.
Okay, and then so if you're going like, oh, this is going to be very small, we can negate that. Then why? Because I'm guessing that
those don't go away, right? The x's, the 0 plus x. So it's this kind of comparison. Let me see. I'm going to erase this answer at the bottom if that's okay. We all agree to this answer? Great. So it becomes this comparative idea of 0 plus 0.0018 versus 0.25 minus 0.0018.
So you're
is
saying
0.0018 big or small compared to 0?
big.
Big. So in this case, that's going to be approximately equal to 0.00. I don't need to do approximate in that case. It's equal to 0.0018.
Okay.
Is 0.0018 big or small compared to 0.25?
Small. So you're basically being like, this is a larger change when you're looking at what you're changing it from.
Yes. So there's a couple places where we could get into trouble. If my initial concentration was really low, like if it was in the micromolarity or the millimolarity range, that x can become really significant. The approximation is bad. Or if my Ka is really quite big, then my x could end up being really large, and the approximation would be bad. Now, in this class, I'll try to only do examples where the x is small approximation is valid. If you take third quarter chemistry, Chem126 or Chem129, whichever one you take, we will get into specific situations where we have to do this comparison and say whether x is small is good or bad, and kind of do that analysis of like, was it good or was it bad? And the reason that I'm okay with that is because if the approximation is bad, you just got to go solve the quadratic or the fifth root or the sixth root, depending on like how complicated the equilibrium is. Because we did have an example in class Thursday where it wasn't just a quadratic, it was a fifth root equation.
Okay.
And by doing the x is small approximation, it was just like divide and take the cube root. Made it way easier. And so that's what we're looking for, is just ways that we can simplify using the reality of the physical world and the kind of the constraints of our physical system to say, and our knowledge of chemistry, to say, we don't need to do all that math.
Okay.
Now, in biochem, in biology, these types of approximations become really important, especially in bio classes. They make the x a small approximation, but they do it without explicitly stating it. They're like, oh yeah, solve for pH, use this equation. The equation they use has the x a small approximation built into it. And sometimes fails because if you don't realize you're using the x a small approximation, you do your calculation, it comes out wrong, and you're like, I don't understand what's going on. It's like, oh, your initial concentration was so small that your approximation failed. And so I was really frustrated when I took this bio class because we learned to use this equation, we use this equation, we use this equation, and they were like, oh, not in this case though. And I was like, wait, what, why? Oh, we've been using an approximation, and they didn't say it. They're like, oh, because it's too low concentration, was all they told me. And I was like, okay. And then I took a chem class, and I was like, oh, this is that thing. So I try to make it explicit, right? You know, it's like, it's not because I said so, it's because an approximation failed. It's like, oh, we have to use a different equation at low concentration. You have to solve the quadratic at low concentration because the x is small approximation failed. Whew, that was a little bit of a sidetrack. That was number 18. Other questions about that before we go on? Okay. Number 19.
Okay.
What do we got for number 19? I'm going to switch colors now.
So with an initial concentration of 1 mole A and B.
So this is concentration of A, concentration of B.
Yeah.
1 mole, 1 capital M, 1 molarity?
Yeah, 1 molarity.
Okay.
What is the equilibrium concentration of C for the following reaction?
Oh. What's the following reaction?
A plus B goes to 2C.
Any states of matter, anything?
No, just K is 2.5.
KEQ is equal to 2.5?
Yeah.
I'm going to assume that these are all aqueous, otherwise the problem would be really weird and impossible to solve. Or they're all right, none of these are solids. None of these are pure liquids. Otherwise, the problem is impossible. It should state that explicitly. If this was on a quiz or an exam, I would say all of these are aqueous. Explicitly. Okay, so we've got our initial. We're just going to do... it doesn't say this explicitly, but I'm assuming we start with 0 concentration of C.
Yeah, it doesn't. Well, it says no C. So
Okay, so it does say no C. It says initial concentration of C. Right. So in that situation, I'm going to have 1, 1, 0. I should put labels of molarity on there. Molarity, molarity, molarity. My Q is 0, so even if my KEQ is really small, I'm still going to go towards products. Here, my KEQ is not that small. I'm still going to go towards products. I'm going to have minus x, plus x. I'm going to have 1 minus x, 1 minus x, and x. I'm going to have KEQ is equal to x squared divided by 1 minus x and 1 minus x. I'll just go ahead and plug in KEQ as 2.5.
How'd you get x squared?
Oh, sorry, that's not x squared, it's just x. Oh, because it's 2 c's, it is x squared.
Okay.
Now look at this. Great question. Is 1 small compared to 2.5?
Would it be 2x? 4x squared?
Oh, it would be. Thank you, thank you, thank you. This would be 2x. This would be 2x. This is going to be 4x squared. Almost missed that. Thank you. Trying to go too fast because I want to show you this math trick. Okay. Is 1 small compared to 2.5? Right? So in this situation, I'm like, I don't think the x is small approximation is going to work. Right? We can try the x is small approximation, see what happens. I'm going to get 2.5 divided by 4 square root. 2.5 divided by 4, take the square root. I'm going to get 7.9. If I ignore x, I'm getting an 80% error. Yikes. So then I say, okay, well, how can I deal with this? Solve the quadratic? There's actually another trick we can do. And this is a cool little trick, and it only works in a couple special cases. But I'm going to rewrite this as 2x squared divided by 1 minus x squared is equal to 2.5. What can I do?
We can take the square root.
Take the square root of both sides. So I end up with 2x over 1 minus x is equal to the square root of 2.5. Now we can solve. So that one's just a cool little math trick we can do.
I'm in Calc 3, so I was thinking about like, oh, you could do like cancel out. Never mind.
You're doing like weird,
yeah, right.
You're like
break it up
foiling,
to see if you
canceling, and like all that
I was
stuff,
just thinking of, oh, like you could do the power rule so that it's 4, but then we're not taking the limit of anything, so that doesn't make sense.
Yeah. So you get 1.5 plus 2. So we're going to have 3.5 on that side.
0.4.
If you were to make it,
Yeah, 0.44.
Sorry, keep going.
That's okay.
Um,
It's like a weird week. It's Tuesday, but it feels like a Monday,
Yeah.
and also like a Thursday at the same time. I don't know why.
But if you were to make it like that far on a exam or something, but then you ended up calculating it wrong, would you get
0 points. No, I'm
like,
kidding.
essentially all of the points? Or?
You'd get pretty much like 90. Like if it was out of 10, you'd get a 9 out of 10.
Okay.
If it's a multiple choice problem, that's a little different story.
Right.
But like on a free response problem, 9 out of 10, no problem. So this one was really similar to the last one, but had this weird math trick at the end. Number 21.
The question is, consider the reaction below 2, I don't know what this is, 2In,
2 indium.
2 indium solid plus 3 cadmium 2 plus aqueous goes to 3 cadmium solid plus 2 indium 3 plus aqueous. And
Whoa, hold on. How many cadmiums?
3 cadmium solids plus 2 indiums 3 plus aqueous. And then K is equal to 9.01 times 10 to the negative 4. And then the question is, we make up 250 milliliters of a solution of cadmium NO3, and there's 2 NO3s aqueous with a concentration of 1.83 molarity, and add a 11.5 gram chunk of indium metal. What is the equilibrium concentration of indium ions?
What was that initial cadmium concentration?
You get 250.0 milliliters of a solution of cadmium NO3
What was the?
Oh, sorry, the concentration is 1.83 molarity.
1.83?
Yeah.
Okay. The volume is actually not that important unless we're doing a follow-up question.
Does it matter that it's like cadmium nitrate?
No. So let's think about a couple different things here. I was going to rewrite the problem, but let's think about it instead of rewriting the whole thing. Right? So a couple things going on. Right? What do we know about nitrate compounds?
They're like they can dissolve.
Right? So I know that if I had my 1.83 molarity here, it's going to go to a 1.83 molarity here and a 3.66 molarity here, but I don't care about the nitrate. Right? And that's because it's a 1-to-1 ratio and a 1-to-2 ratio. So all that matters to me is that I end up with cadmium in solution. Now my experimental setup is 250 milliliters with my cadmium solution and a chunk of indium at the bottom. Right? And so the important thing here is, again, that idea of like, I've got this initial setup, the cadmium and the indium are going to interact with each other. It's going to go through a redox reaction, and I've got to do some setup. So I'm going to rewrite this real quick. I don't really need to rewrite it. I'm just going to say no, I need to rewrite it. I need to rewrite it. So let's go ahead and rewrite it a little bit smaller here at the bottom. Otherwise, I was going to try to do it in my head, and I was like, I'm going to make a mistake. And then you all won't see it because like I'm doing it in my head. So I'm going to have 2 indium solid plus 3 cadmium 2 plus aqueous goes to 2 indium 3 plus aqueous plus 3 cadmium solid. My initial, I'm not going to worry about the solids. That's part of why I wanted to put them on the ends. My cadmium is going to be originally 1.8. Whoa, why did I do 2 1s there?
How'd you get
1.83.
3.66 for the 2 and the 3?
I tried to double 1.83 in my head because it's a 1-to-2 ratio.
Oh, yeah. Okay.
But it doesn't matter anyway. Nitrate's not participating in the reaction.
Okay, I was wondering, were you just like showing that as an example, like the nitrate?
Yeah,
Oh,
right.
okay.
So
I
this
was
is
like, where did that come from?
yeah. So this is how it would disassociate. But all we actually care about is the cadmium, right? There's no nitrate in the actual reaction.
Yeah. Okay.
My indium is going to start at 0 concentration. Then my change is going to be plus. I have to use up my cadmium. I have to taking mole ratio into account. That would be minus 3x. This would be plus 2x. And I'm going to have 1.83 minus 3x. I'm going to have 2x. Then my KEQ, which is going to be products over reactants, is going to be indium 3 plus squared divided by cadmium 2 plus cubed. And now I plug everything in. I'm going to have 9 times 10 to the minus 4 is equal to 2x squared divided by 1.83 minus 3x cubed. This is going to be a 5th root equation. You're going to get 5 different x values where only one of them is valid. We could do that in our calculators theoretically. Like anyone with a smart enough calculator can theoretically do this. But I use these not so smart calculators that I really like, and we had some problem using our smarter plus like 5 amps. We just use the x small approximation if we can. Do you think we can in this case?
It seems pretty small.
Yeah, my K is 9 times 10 to the minus 4. My initial concentration is 1.83. I'm feeling pretty good about it. So I'm going to go ahead. Question?
Sorry. At what point would like the coefficients in front kind of make it not so small? You know, like, or is that just up to your kind of your own judgment?
So we're going to do own judgment. What I like to do, so the textbook has this example. Was it already 2? I gotta eat and get ready for class. The textbook has this example of like, oh yeah, we still have class today. It's not Monday.
Right.
Oh, jeez. Yeah.
I do that all the time. I check my fake watch.
There's lots of situations where it could be a problem, right? And so what we're going to do is we're going to use the approximation and check if it was good or not, right? The fact that it's 3x, the fact that there's the cube root here and a square root, like there's a lot of things that could get in the way of this being a good approximation. The textbook has an example they do where they're like, oh, if the ratio is less than 400, you're good. And it's because it's 0.05 inverse is 400, so like a 5% error but flipped over would be 400. They have this whole system, only works for a 1-to-1 mole ratio. And so when we're doing things that are like 3-to-2 mole ratio, it's really hard to have like a pre-check.
Right.
So we're usually just going to eyeball it and say, I think it's good. Let's calculate it and check after.
Okay. So
we're going to go ahead and do 9 times 10 to the minus 4 is approximately equal to 4x squared divided by 1. Ooh, that's really scrunched there at 1.83 cubed. X is equal to wrong. 1.83. Oh, I forgot my decimal point. I was getting millions. Times 9 times 10 to the minus 4. Divide by 4. Square root. 0.37. Is this solving the whole thing out right?
Yeah.
0.34, right?
Yeah.
So from your answer on there, we can do a actual percent error
Yeah.
calculation of
It'd probably be
0.034
less
versus
than
0.037. So let's see here, negative plus 0.034 divided by 0.034. Our actual percent error, wow, that's actually a pretty significant percent error. Unless I did my quick percent error calculation wrong. It ends up being like a 7-8% error.
Really?
Yeah. Our percent difference looks fine though, right? So if I do 3 times 0.037, right, I'm going to have 1.83 minus 0.1. It should be like a 5%. I'm getting like a 5% difference comparing the 3x to my initial concentration. So in terms of our approximations, we're fine. We're fine. It's approximately correct, 0.037 versus 0.034, assuming you didn't make any typos, but I believe you. So that's how we do that one. It really is the same. Like, the thing that's nice about this problem is when you look at it, it looks so much more complicated. But when you get down to it, it's initial change, equilibrium, x is small approximation, we're really still doing the same steps. Okay, I know there's one more question on there. We'll have to do it tomorrow during office hours. I'm going to go ahead and stop this.